Any thoughts on the recent legislation on crypto passing the House? Not yet. I have to talk to our government affairs people and kind of think about it. Have you ever considered donating to Huberman's lab? Not really. I think he plans on funding others' research and not his own anymore. The single biggest waster of money is academia. And when you throw money at them, unless you understand the people and you have tight controls and you know how to run the research process with them, you'll see 20 million turn to 10, turn to 5, turn to 2. For example, the endowment for the CMU side of things, there's a tight budget there. It's only about $1 million and so a year from the endowment that I set up, but that's perpetual. And there's a really good leader there, Jeremy Epicad. He's grown enormously in his role, and he's had a huge impact with a modest amount of resources. It would be catastrophic if the budget was $10 million or $20 million. And the problem right now is a lot of this biotech research, it's bloated. And guys, it's not an R&D problem. It's a clinical trial problem. So here's an example. Very recently, there's a prominent researcher at Harvard. His name is David Sinclair. And David just published this amazing paper that's kind of inspired by the research from Yamanaka factors. And he came up with a collection of 6 chemicals that if you sprinkle into a human in just the right way from in situ from cell cultures that they had, it actually reverses aging according to some metrics that they have. Now, it has to go through the peer review process, and people have to confirm and replicate the study. And of course, there's a lot of criticism here and there. But the point is that that's an extraordinary result that I can just sprinkle some chemicals on cells and make them younger. And it could be systemic, meaning that every tissue type, your bones, your brain, your heart, and heal you. Okay. What's the problem? The problem is to go from that to a drug I give you, minimum 10 years plus, $250 million. Why? The limiting factor is the clinical trial. The limiting factor is the IRB process. The limiting factor is the human being and the doctor in that. So I built a clinic in Gillette because that is the single biggest skeleton key to that. And if you can vertically integrate and figure out how to do great studies, as we're figuring out right now, then you're friends to all these research groups like the Sinclairs of the world, the Buck Institutes of the world, and the dozens of others like Calico that are working on some notion of anti-aging, because you can actually take that drug and figure out how to test it on people in an ethical way with a keen eye on safety. So build that. The problem is a scientist is not a physician. It's a very different thing to think about. A scientist doesn't touch people, doesn't treat people, doesn't deal with realities of medicine. They deal with cells and microbes. They deal with bizarre scientific formulas on a wall. They deal with chemistry. They deal with receptors. They have to do the hard, heavy lifting and thinking. And there are millions of them throughout the world. And they are incredibly well funded at the moment because every billionaire wants to live forever. That's my generation's white whale. They're chasing that. But they don't focus on the things that actually can accelerate that stuff to market. That's the difference between the Neuralinks and the Synchrons. Neuralink is started by a Silicon Valley billionaire, and it's been a long and brutal and arduous road to get to a clinical trial. And still, ultimately, what are they doing? Drilling holes in people's head and putting things in. Very direct way of doing something. Synchron is, oh, well, doctors have been putting stents in forever. Let's just put a stent into the brain that can read brain waves. Super easy to put to the neck. Okay, it's like a 10-minute procedure. Doesn't need a neural surgeon. Physician can do it. Synchron's already done a clinical trial. They've already put the devices in humans who are right now today think to text ALS patients. Why? Because it was started by an MD PhD who understands medicine and understands the realities of medicine and how to actually do medical research and get things through the approval process. So you have to understand those nuances, and you have to understand where there are inefficiencies and where people waste things and what people do. You know, the other thing too is you have to be very realistic and reasonable about how to approach good research. So you have to be intellectually honest about where you're getting strong signals and where you're not. And you have to focus. We have a strategy at our clinic that I think within the next 24 months will result in an anti-aging product that's extraordinary. Requires a doctor's supervision. It's complicated, but I think it's going to be far beyond where the market's at right now. It's not because we're smarter than everybody else, but just because we took a very first principles approach, had a 360 view of the entire market, and we took a step back and said, you have two things. You have to put the body in the right condition to regenerate. So there's a signaling and epigenetic notion to that. And you have to have the right ingredient that the body knows what to do with, that when you combine them together, it works well. The Sinclair research is certainly attempting that, but it's a foreign substance. Requires FDA approval. There's an entire invasive set of things that need to be done. And if you look at the lead author of that paper, one of them wrote a prior paper talking about the cytotoxicity of one of the substances they're injecting. So it's like, is it real? There's a lot there. You have to deconstruct that. It's a process. And I've done science for a long time, over 10 years now, 180 papers published under my watch, running IOG, running labs, these types of things. I know my critics like to say I'm just a big dummy. I don't know anything. And I just somehow magically stumbled my way to incredible success. But it was hard earned, and I had to kind of understand what was going on and make decisions in the room. And managing scientists, managing the scientific process, managing academic relationships, and having those result in papers, which now we have more than 10,000 citations for in a peer-reviewed process, is probably one of the things we're pretty good at. And yes, there are clear differences in the biological world, but not as many as you'd think, for the nature of academia and how these types of things work. So we're pretty good at how to build good science. And that's what we do. But we're also good at figuring out a research transfer of how do you get science out of the lab into the market. If you look at Cardano, there's so many things that took a very long time. And our critics point that out. But what they don't mention is there's so many things that should have taken a lot longer that we were able to get out a lot sooner, because we figured out a much easier and better way to do research transfer. So just think of it. How does a room temperature semiconductor, a superconductor, impact Cardano? The biggest impact for cryptocurrencies is that room temperature superconductors, if they exist, so ambient pressure, ambient temperature superconductors, that would be a major step forward to make quantum computers easier to manufacture and scale. Now, there are many other use cases. We lose like a third, I think, or more of our power just from losses on transmission lines. There's all kinds of things related to building fusion reactors and this stuff that superconductors would be amazing for. So energy revolution, maglev trains, you name it, we got it. It's an incredible advancement. It would be the most significant scientific advancement in the material science world of our lifetime if we have room temperature superconductors. But for the purposes of computing, the most significant thing is superconductors are used in the construction of quantum computers. And this would massively simplify the design of them and also enhance the fidelity of computation. It's not just about raw qubits. It's as you scale qubits up in the system, you also have to scale up your error correction capabilities, because the probability of a calculation failing goes up. You have superconductors that are room temperature. It's a whole new ball game on the fidelity of computation, which means that many, many qubit systems are now in grasp. And if that's the case, then you can apply quantum algorithms that have been developed in the 90s and 2000s to start compromising the fidelity of cryptography, which would have catastrophic consequences on national security and cryptocurrencies. So if such a material existed, it moves the clock forward. It's kind of like when you're building nuclear bombs. If you don't really know how to do implosion and all you have is uranium-235, you might be able to build one. We did with Hiroshima, the gun design, two pieces of uranium smashing into each other. But if you do know how to do implosion and you have access to plutonium-239, you can mass manufacture them, which is exactly why there's 70,000 nuclear weapons floating around, and they're very reliable. So these types of innovations are huge, and they open up new possibilities, both dystopian and utopian.